Welcome to the Chandara Academy. Today we are going to solve an exercise from chapter 1. This exercise is about arithmetical geometric sequences. So sequences with the form un plus 1 is equal to a times un plus any constant. So in this exercise we will try to find the explicit expression of un. So we've got un plus 1, which is equal to 3 un plus 4 for all n greater or equal to 0, and u the n is equal to 0 is equal to u0. Okay, so now we will try to solve this exercise by two manners, so two ways of having the solution. So first one which is very specific to this kind of sequences. Okay, so we will try to find first the fixed point of this sequence. So a value that satisfies x, so we replace un plus 1 and un with x, is equal to 3 times x plus 4. So we solve this equation. We have minus 2 is equal to 2x, minus 4 is equal to 2x, is equivalent to x is equal to minus 2. So now that we have this solution, we will study the behavior of Vn is equal to un minus x for all n. Okay, so is equal to un plus 2, and we will see why studying the sequence Vn is very important. So let's try to give an expression of Vn. So Vn plus 1 is equal to un plus 1 plus 2. We said it is equal to 3 times un plus 4. So this is the expression of un plus 1 plus 2 is equal to 3 un plus 6. And let's factorize by 3 is equal to 3 times un plus 2. And here we have, and this is not chance, but we formed Vn to behave like that. We have here the expression of Vn. Okay, so this one. So we conclude by saying that Vn plus 1 is equal to 3 times Vn. So the sequence Vn is geometric. Okay, and we have V0 is equal to 3 to u0 plus 2, to u0 plus 2. And we know how to deal with geometric sequences. Vn is going to be easily V0 times 3 to the nth power for all n. And now that we have the explicit expression of Vn, let's remember that un is equal to Vn. So un is equal to Vn minus 2. And so un is equal to V0 times 3n minus 2 for all n. And let's give an expression of V0. V0 is equal to u0 minus 2. Okay, is equal to u0 plus 2, sorry. So we have, in conclusion, un is equal to u0 plus 2 times 3 to the nth power minus 2. And here we have our solution. So this was the first method, a method that always works with arithmetical geometric series. Then we will solve this problem using the second method. So let's remember that un plus 1 is equal to 3un plus 4. Yes, for all n greater or equal to 0, and u the n is equal to 0 is equal u0. Okay, so now let's use the second method. The method you know how to use for recurrent sequences of order 2 or more. Okay, so we will have un, the solution, which is equal to un star, which is the homogeneous solution, plus us, which is going to be the singular solution. So let's try to understand a little bit what's going on. Okay, so un star, the homogeneous solution, will be the solution of un plus 1 is equal to 3un. So we only keep the terms in un. Okay, so this is going to be the solution of this equation. So let's find it. So we have un plus 1 minus, so characteristic polynomial, we're going to have r is equal to 3. It implies that un stars will be equal to a constant lambda 1 times 3 to the nth power. Okay, and then when we have that, we are going to find the singular solution. So the singular solution, which we are going to add to the homogeneous solution to find un, is going to have the same look as what's after the un terms. Okay, so here we have a polynomial of order 0. So a polynomial function of order 0. Otherly said, we're going to have a constant. And so we are looking un has the form of a polynomial function of order 0. The same form as 4. So this, if it was a polynomial of order 2, we would have u singular, a polynomial of order 2, etc., etc. And so we will call it, we will try to find un is equal to k. Okay, so let's try to find the value of k. So we remember that un plus 1 is equal to 3un plus 4, and that u singular is the solution of this equation. Okay, so let's replace un with un singular, and so we have k is equal to 3k plus 4, and so we have k is equal to minus 2. And to conclude, we have un is equal to u star plus u singular is equal to lambda 1 times 3 to the nth power plus, so minus 2 plus k, so minus 2. And now we will use the boundary condition u0, u the n is equal to 0, is equal 0. And so we will have u u0 is equal to lambda 1 times 3 to the 0th power is equal 1 minus 2. It implies that lambda 1 is equal to u0 plus 2. And so we conclude by saying that un is equal to u0 plus 2 times 3 to the nth power minus 2. So this is a method that always works, okay? For order 1, for order 2, so here we have order 1 because we only have un plus 1 and un, but if we had un plus 2, un plus 1 and un, we would use this method, the exact same method. And so we have a conclusion. We can see that this result is the exact same one than the one found with the other method. And so we have finished this exercise. Hope you enjoyed the video. Bye.